I'd like to remind everyone that audio is provided via the internet. Let me check status screens. Everyone looks good. You should be able to now hear the audio. I'd like to remind you that there is a Q&A tab at the top of your screen. Please use this at any time to type questions that you may have. I'll monitor the Q&A bar and hopefully answer your questions quickly. Our web seminar today is on collecting good field failure data. I think good field failure data is something a lot of people are very interested in. And I would just tell you up front that I have had the opportunity to look at dozens of field failure data sets for purposes of analysis, and there's a lot of work to do. But we'll talk about that today. My name is Bill Goble. I've spent many years in the world of reliability engineering and safety integrity analysis. For the last 12 years, I've been with a company called Exida. Exida is a global corporation. Exida is an accredited certification body, and the certification group does both product certification and personnel certification. We have a consulting group that does systems level consulting, primarily for end users in petrochemical power. All groups do training, and we have a product group that does engineering tools and maintains a database. Many different engineering tools have been created at Exida, and I'll be talking a little bit today about the SIL-STAT data collection tool. I specifically want to say that one of the tools available from Exida helps you do field failure event database creation. And if there's any interest, be sure and let us know later. Exida is a very technical company. I'm proud to say that people from Exida have authored or co-authored most industry references in the world of automation and safety. We develop procedures, we do research, and then we publicly publish our procedures. We publicly publish our data. We want to make the world a technical, safer place. All right, let me check status screen one more time. Everything looks good. Okay. Remember, don't forget about the Q&A. Now, today we're talking about field failure data collection. Okay, why in the world would anybody collect field failure data? Well, we are looking for problems. One of the most obvious uses of field failure data is to look for application and instrumentation compatibility issues that lead to high failure rates. Many of these failures will cause a process trip. We look for problems that reduce process uptime. Why? What we're really trying to do is save money. Many people need this data to justify prior use selection of equipment. The data can be analyzed to see if plant failure rates actually match the data used during your LOPA or PFD calculations. And there are many opportunities for maintenance improvement. And again, why? We're trying to save money. This isn't just some regulatory requirement that some government says you must do. The reason to collect field failure data is to save your company money. And that's a very appropriate reason. Now, you probably remember the fact that IEC 61511 is based on two fundamental concepts. At Exida, we think of it as a detailed engineering process designed to prevent systematic failures or design mistakes. And there's a probabilistic performance-based system design allowing us to deal with sufficient safety integrity against random failures. The safety life cycle is a series of steps taken during the analysis, design, and operation of a safety instrumented system to reduce design mistakes, increase safety, and optimize cost. Today, what we're talking about, to the great extent, is how to optimize cost. Now, there are ways to do that, and there are ways not to do it, but we'll be talking about that today because, remember, the objective of all of this is to help us reduce cost. Besides, how in the world is management ever supposed to approve something if you don't show them how they're going to get a return on investment? At Exida, we think of the safety life cycle in 3 phases. During the analysis phase, we figure out how much safety do you need. Now, we're not going to get into the details of the analysis phase today, but normally it involves identifying hazards, figuring out how likely they are, comparing that to tolerable risk criteria, and creating safety requirement specifications. Well, that's obvious. We don't need field failure data for that. Oh, but we do. We could really use event data in determining what are the potential hazards. If we have historical data, we can do a better job at identifying potential hazards. And in fact, we'd like to know failure probabilities of many pieces of equipment if we're doing layer of protection analysis in order to optimize safety integrity level targets. And we certainly want event data to help us estimate consequences. So in fact, although you could certainly use industry databases, you really need to have a very good understanding of what are your hazards, what are the consequences, and how likely are they. Now, during the realization phase, which is where the safety system gets designed, we figure out how much safety does my design actually have. And of course, this is where we pick our equipment, we pick levels of redundancy, proof test procedures, and of course then we do calculations. Do you need field failure data for that? Well, failure data might be unbelievably useful for that because field failure data might identify potential differences between industry databases and the actual numbers in our plant. How about operations phase? Oh, and of course, if you're doing prior use justification to select your equipment, you really need failure data to justify the equipment. Just read the requirements of 61511. Now, for those of you who are interested, Exida did a web seminar on that a week or so ago, and all of those web seminars are available as recordings on the Exida website. I don't see any questions or answers yet. Don't forget. All right, the last phase of the safety life cycle is the operations phase. Now, this is where we test our safety systems and then introduce them into service, including, by the way, don't forget that cybersecurity audit these days. Cybersecurity threats are indeed credible. Do you need any field failure data for this? I mean, yeah, I don't know. What would you use field failure data for? We're determining how will I keep the plant safe, and in fact, we did calculations in the realization phase to determine proof test intervals. We may very well have failure rates higher than those assumed, in which case we're not getting the levels of safety that we expect. Or we might have failure data which indicates we don't need to do the proof testing quite so often. This failure data can have a nice payback if you can justify reducing the proof test interval. So there are many reasons for collecting field failure data. I hope you now have a good understanding of the incentive behind this. Remember, we're trying to save money. So let's take a look at what kind of systems exist and what kind of systems should we have. I got a chance to look at some field failure data. It was from a test shop doing proof testing. And the results record number of units in the field and number of operational hours were well recorded, and the number of units that failed the proof test, which was done every year, the number of units that failed the proof test was carefully recorded. And that data was analyzed to come up with a failure rate. And this particular shop had particularly low failure rates. Of course, that is a red flag. An on-site visit to the test shop showed that their procedure involved cleaning up the instrument before testing. And in this case, cleaning included disassembly and replacement of seals and O-rings. In effect, they completely refurbished the unit before determining if it failed or not. It's surprising that any units failed after that refurbishment activity. So in fact, this particular procedure was quite flawed. As found conditions must be recorded in a proof test. So there's one of the first and most important things about any field failure data collection system. And of course, anybody analyzing the data must thoroughly understand the data collection process in order to judge the validity and to have confidence in any data set. In another field failure study, an owner-operator repair shop had maintenance data recorded in their maintenance management system. That maintenance management system printed out a list of estimated operational hours and and number of failures, and in this particular case, this maintenance management system recorded or calculated failure rates, and the instrument engineer saw that the failure rates calculated by this particular system were much lower than those used during the SIL verification. The failure rates provided by the SIL verification tool, Excellentia, were much lower. So obviously, the proof test intervals could be extended with no impact on safety. And there was, wow, nice opportunity to save a lot of maintenance expense, right? However, before proceeding, the instrument engineer visited the test shop. Remember, I said that someone must understand data collection procedures before having confidence in the data. It was discovered that failure reports were entered into the MMS system only when a device was sent out for repair, because that's how the repair purchase order was generated. All the units that were repaired internally were not recorded as failures because no purchase order was needed. That's obvious. I mean, why would we type this into the machine if we don't even need a purchase order? Oh my goodness. The data in the MMS, the number of failures, was quite optimistic. And therefore, the data could not be used, and the proof test interval was not extended. Again, one of the most important attributes is the as-found conditions during a proof test must be recorded. And of course, the test, repair, and data collection process must be understood in order to analyze any data set. There's more. Oh, I have dozens and dozens of stories, but you don't have time for all of them today. A detailed study of a valve showed a low failure rate when compared with the exida Predictive Analytics benchmark. Our conclusion was this particular valve would be an excellent choice for safety applications, and the sales department of the valve manufacturer got very excited. The valve was designed and manufactured for control applications. Okay, fine. What's the difference between an environment for control and an environment for safety? The report did not give the operating conditions, so one could not verify But it's very possible that data had been gathered for the dynamic operating conditions of a control valve. In other words, the valve moves a lot. Failure rates for the same product in a static application would be much larger, as many failure modes such as stiction, cold welding, corrosion binding can't exist in a dynamic application. Next important lesson, application conditions must be recorded and listed in any analysis report. Else, how would one know whether the data could be used in another or different application? So, after many years of reviewing field failure data sets, many of the things that became important to a data collection system, many of the things that are important to a field data collection system became apparent. It's very important that anyone who analyzes data thoroughly understand when a failure report is written. It's very important that any data analyst understands what's the definition of a failure. In some cases, and particularly with manufacturers, their definition of failure is quite different than the end user. As found conditions, we must ask the question, are as found conditions recorded during a proof test? And of course, what were the operating conditions? As you begin to thoroughly understand these field data collection systems, of course, one can refer to standards that have been written. And the 2010 version of IEC 61508 specifically lists ISO 14224 and IEC 60300-3-2 standards on, or application guides at least, on collection of field failure data. And obviously, when you read through those, you'll see that it's pretty much common sense stuff. But they've done a pretty good job of listing all the things that are important for a field data collection. So most of the things that are important for a field data collection system. And then if you throw in the AICHE PERD Database Committee, Taxonomies and Software, that's also valuable input to a good field data collection system. A lot of people have spent a lot of time studying this problem, including people at exida and outside, and the rules and the concepts are becoming pretty clear. A good field data collection system must adequately identify components, record operating profiles and physical environments, record the volume of operating experience, know any proof test method and the estimated proof test coverage, and in the case of accurate calculations of PFD averages, you must track actual bypass time if, in fact, the safety function is disabled during a proof test. Think about that. Some proof testing does not disable the safety function, but some does. So that's an important parameter that needs to be tracked in order to more accurately calculate PFD average. Now, those are things that are important technically. Those are pieces of information that must be known. But there's some other things that are really important that really aren't talked about very much. I've always been told if you want somebody to do something, make it easy for them. So it should be very easy to use with minimal to no added work for maintenance people. I spent one summer working in the maintenance department of an industrial plant. And I have to admit, we got things done, more likely got things done on schedule when they were easy to do. And it sure would be nice if we could actually devise a system that takes less man-hours than current methods. We are actually trying to gather up field data to optimize and to save money by improving uptime and reducing failures and identifying application instrumentation mismatch. But it would be great if we could set up a system to do that that doesn't really cost any more, or perhaps even costs less than the current methods that are being used. Well, what do we mean? Let's dig into this in more detail. What do we mean by adequately identifying the components? A really good system will identify for every component the manufacturer, the model number, and the serial number. That way, if an instrument moves from location to location in the plant, we can still track its reliability history. Now, I am talking a really good system here, so don't panic yet. What do we mean when we say recording operational profiles and physical environments? Well, where was the component installed? What are the physical conditions of installation? What's the tag number? What's the unit number, plant, site, and company? Now, that's just a hierarchical identification that provides a unique identifier within the context of the system. If you know the physical conditions of the installation and the tag number of the installation, the unit, plant, site, and company, we can uniquely identify where this is installed, and by knowing that, we can understand the operating profiles and the physical environments. We said we have to record the volume of operating experience. Volume of operating experience. I immediately think of a bucket and filling it with water. And what's the volume in the bucket? No. We're talking about unit operating hours. How much time does this product operate? Now, we really should have the commissioning date, any decommissioning date, and the operating duty. I mean, is it a simple 24/7 where the instrument is basically on all the time? Or do you only turn it on 1 or 2 hours a day? I mean, think about a typical automotive environment. With my car, I mostly drive it to work in the morning, a half hour, and then I shut it down. I drive it home in the evening. I run for a half hour and shut down. I might go out or run errands for an hour or two in the evening. So worst case, we're talking 3 hours every day, not 24 hours every day. So record the operating duty and whether it's continuous or intermittent, because that has a lot to do with various stress factors that influence the reliability of the components. Now, what kind of events should we track? Well, there are many different event types. We really do need to track results of each proof test, not only to show that we've done the proof testing, but to calculate failure rates when the as-found conditions are recorded and when failures are therefore identified. A diagnostic event. What if an automatic diagnostic in a pressure transmitter or a logic solver or even a partial stroke valve test indicates a failure? Well, we need to record those also. That's kind of like an automatic proof test. Except with the diagnostic, you usually get an error code that gives you a pretty good idea of what's failed. You need to track process demands, actual trip events. That's valuable information during the layer of protection analysis. And we need to track process upsets or false trip events. I've seen some good data collection systems that rely on proof test results. Now, the problem with that, of course, is you're missing all the false trips. If you want a good picture, and if you really do want to save money, we have to work on in fact, most people really want to work on the false trip events. What needs to be recorded? The event type, person performing, the date and time, any particular device is removed from service, the date and time it's restored to service, and of course there are other pieces of data depending on the event type. Okay, knowing this, let's take a look at the particular data for a proof test. You need to know what device failed. You certainly need to know as found conditions, and if possible the failure mode. How did it fail? I mean, if you just go out and try to do a calibration and you check, the first thing you do is check to see if it's in calibration. Let's say it's not. Well, that's a failure. It very well could be so far out of calibration that it could have not responded to a process demand. That's the definition of dangerous failure. So you write that down as the as found conditions. And the failure mode was out of calibration. What's possible cause? Many say write down any opinions of what might have happened. Others say no, people who record the data should only record facts. I'd like to say go ahead and allow somebody to express an opinion. That's okay. Failure date and time, the person who did the replacement or restoration work order number, and the date, time that the safety function or the instrument was restored to service. Make sense? I haven't seen any questions yet, so please, anything I say doesn't make sense, ask a question. One of the important things about reducing the amount of work is every time there's an event, you really do wish to reduce the amount of information that must be typed in. One way to do that is to set up a tag database. One very clever approach I have seen is that every instrument has a tag. The tag has a barcode. Barcode scanner hits the instrument and knows a lot of information immediately, like the instrument tag, the model number, the manufacturer, the sensing element if it's not part of the purchased model. You can buy a temperature transmitter, for example, and not know whether it's an RTD or it's being used with an RTD or a thermocouple. The serial number should correspond to the instrument tag. What unit is it installed in? How is it calibrated, which gives you some information, even about the environmental limits, perhaps. The commissioning date, the decommissioning date, a typical environment, and one of the easiest ways to do that is simply a pick list. It's field severe, it's control room. Keep it simple. You can have a lot of information with a very simple categorization scheme. It's a temperature transmitter and it's operating 24/7, 100% of the time. That's a great collection, a data collection tag database. Now, what about the event data? Well, you certainly need to record all events, proof test results, maintenance and repair actions, and process demand. Now, the needed information depends on what kind of an event it is, and so normally the question lists and the pick lists will change depending on event type. Remember, a fundamental concept is avoid unnecessary data entry. Gather the information automatically whenever possible. Checking status screens. Okay, everything still looks good. How does the information get collected? Well, for every event, for every piece of event data, which includes the event type and the failure mode from a pick list, possible cause from a pick list, failure dates, who did the work, primarily so you can go ask questions if something doesn't make sense, work order number, date and time removed from service and restored to service. We take the event data and correlate it with the particular tag data of the instrument that failed, combine these into an event database. Now, in the exida system, the event data collection and evaluation system gathers up the combination of an event and a tag set of data. So tag data is only entered once. At setup time, event data collection is minimized, and the combination provides an excellent set of data for failure rate and event database, or data analysis, what I was thinking. All right, any good data collection system has to have a mechanism to review and edit the stored event data and tag data. And of course, typically the procedure is some knowledgeable person will review the raw data before it's sent to an analyst. How do you analyze this data? Well, there are many common analysis techniques that have been developed years and years ago. There is the classical failure rate analysis formulas where the time to failure is recorded for each component. You can see how to do that in the ISA book that I have written, available from Amazon, Exida, and ISA, reference number 1. There's a whole appendix on how to do that calculation. Problem with that calculation is that the sufficient data is rarely available. What if somebody didn't enter the serial number? What if the instruments are mixed up? There's many things that could go wrong that would prevent this classical failure rate formula from really working. But there is the quantal response method. Got a question? Thank you. How is event data entered? Okay, let me go back. Event data could be entered onto a sheet of paper. You don't need any sophisticated system. In the Excellentia or the SILSTAT software, event data could be entered onto an iPad or an iPad 2 or a laptop. And there are even intrinsically safe laptop computers. So you either enter it on a piece of paper and transcribe it to a computer system, or enter it directly into the computer system in the field. Systems that I find work best, the person doing the work has a facility, a means, to enter the information directly into the computerized program. That way, the person doesn't have to do any extra work. What we're trying to do is reduce man hours. A good question. Thank you very much. Of course, there are good analysis methods, even for incomplete data sets. The quantal response method is a statistical curve fitting technique. I read about it in Applied Life Data Analysis by Wayne Nelson. He still gives seminars at the Reliability and Maintainability Symposium, so I like it a lot. He's still retired but active. At Exida, we use the Predictive Analytic Analysis method. Now, this is a more detailed analysis method that we have developed based on using detailed design knowledge. And I will say we are fortunate enough to have studied literally dozens of different manufacturers for virtually every different type of design. For example, pressure transmitter. We know and understand fundamental design details for probably 50 different designs on the market today. Now, how did that happen? Well, the Exida Certification Company does detailed failure mode effect and diagnostic analysis, which gives us failure rates, failure modes, and useful life for each specific design. When you look at the set of designs and put them into a tabular format, you start getting a very clear picture of total failure rate range for a pressure transmitter, failure modes and failure rates for each mode, and a useful life range. So we can say for a pressure transmitter, the failure rate should be between X and Y. All right, now, why is that valuable? All right, I got another question. Thank you all very much. Question is, if you have been proof testing every 12 months and collecting data suggesting proof testing could be extended to 2 years, should this change be done in steps? Is there a calculation to work out the step increments made? That's a good question. The bottom line is, based on mathematics, you could make the change to the new value. Now, I personally like a more conservative approach and would certainly recommend that you take it in a stepwise approach, but there's no math or no method to work out the increments. That's simply judgment. And it has everything to do with how good is your data. And that has everything to do with, in my opinion, getting that data analyzed by someone who thoroughly understands the data analysis techniques. Mathematically, there's no reason you can't move to the new value. If you have high, 90% is what 61508 suggests, high, 90% plus confidence in your data. Another question. Thank you, folks. Obviously, end users will have real life failure rates. Oh, yeah? I have audited about 50 different companies, and nobody has had real life failure rates. Well, sorry, one. So I don't know about that statement. They have sets of data, but what can the engineering... That's not your point. I just want to warn you, end users may or may not have real life failure rates. I hope someday they do, but right now, I don't know. So what can the engineer contractor do since he or she will not have access to real-life data? I assume you mean during the realization phase of the safety life cycle. Well, that's no different than systems consultants at Exida. We use the specific FMEDA results if we know the specific manufacturer and model number, or we use the generic failure rate results if we do not know the specific manufacturer and model number. And Exida generic failure rate data basically assumes worst of class, so that'll be a higher number. If you use the Excellentia tool, which models maintenance capability, FMEDA data is an excellent choice for the initial design. We just did a webinar on FMEDA data, and we do explain in that webinar that, in fact, excuse me, I'm just checking something, that in fact FMEDA data is product specific, not site specific, so it doesn't include maintenance failures. But the Excellentia program takes care of that with the maintenance capability modeling. So in any case, I'd love to see more field failure data. I'd love to see end users eventually get real life failure rates. In the meantime, I think FMEDA data is 20 to 50% conservative, and that's an excellent source for purposes of the initial designs. Another question, does Exida data tend to be more conservative than end-user field data? The answer to that is yes and no. That's a good question. Thank you. Exida FMEDA data is calibrated to be more conservative than real field failure rates attributable to a product. Now, what in the world is that weasel word? If you don't know that phrase in the United States, it's a term where you're trying to avoid explaining something, but I am not. What I mean is all failures at a particular site are due to inherent failures of the product. Some of them are due to inherent failures of the product, and some of them are due to maintenance-induced failures. Human beings cause the failure. And we did have this was covered in the FMEDA seminar last week. You can see a copy of that, but the bottom line is at exida, we use FMEDA data, which is more conservative than real-life data. Plus, we model maintenance capability and site-specific failure rates separately. Because I'll tell you, I gathered up one set of field failure data over a period of many years for the exact same product. The failure rate varied by about 2x from site to site. Did you hear me? I said 2x. Why? We traced down many of these failures by going on site and interviewing the staff. And it was crystal clear that some of these people were far more competent and had much stronger maintenance capability than others. And why would you want to penalize those with higher failure rates? So FMEDA data does not do that. What it does do is allow us to create a predictive analytic model of the product failure rate data, and we use that to analyze field failure data. When the field failure data comes in, we do statistical signature analysis, and we compare the results to the predictive analytic benchmark. If statistical signature analysis indicates a value within the accepted range, that means you have pretty good confidence in your data. If it doesn't, you must find the source of the differences. Of course, that's how we originally identified the maintenance-induced failure rates. So I think the predictive analytic models are just very valuable for checking integrity and developing confidence in field failure data. We often do comparisons between the data set and the FMEDA on a product basis, and any differences, we find the reason. I did provide you a reference on statistical signature analysis, a method developed by Dr. Julia Bukowski while working for exida. Oh, good. We're right on schedule. I very much appreciate the questions. Let me just check and make sure we've got them all. So far, all questions are answered. The bottom line, and the message I'd like to leave you with, is that a good data collection system can be implemented without spending a lot of money. I know there are systems out there that cost a lot of money, and I'm pretty sure they're good systems, but you can implement a good system that will get you a lot of good data without major expenses. The predictive analytics technique is an excellent way to build confidence in your data, and it's the kind of confidence that I think you need before you start doing things like extending proof test intervals. I mean, what if your data collection process was like one of the examples I gave? Simply not getting all the failures. So, we ask ourselves, why collect field failure event data? We are looking for application and instrumentation compatibility issues which cause excessively high failure rates, typically due to a site-specific installation error. We might be gathering field failure data to justify the prior use selection of equipment, especially if we don't purchase certified equipment. We might be using the data to check to make sure that the failure rate data is used by that engineering contractor have a reasonable match to our site-specific data. Maybe we'll discover that we have poor maintenance capability at our plant. Maybe we'll identify a huge opportunity to reduce costs by improving our maintenance training or our maintenance culture. Maybe we can find a way to increase those proof test intervals and substantially reduce proof testing costs. And of course, it's not just about safety. It's about false trips. I've been in some situations where the cost of a false trip was unbelievably expensive, especially when a plant is running at or near capacity. The bottom line is we collect field failure data to save money, especially considering process uptime. So the key to success in any data collection effort is to gather sufficient data to not only improve safety, but also to reduce false trip rates and make sure the system properly pays for itself. Anybody else have any other questions? I'm just going to check the log here. All right, I don't see any others. I'm going to type my email address up here at the top. If you have any questions, even tomorrow or next week, any comments, please do not hesitate to send me an email. I can answer them asynchronously. Sometimes I get a little behind, so don't be concerned if it takes some weeks for me to answer. But I very much would like to answer all the questions. If you have any other questions about data analysis, about the predictive analytics methodology, or the exida databases, don't hesitate to let me know. I do want to thank you for your time this morning. I hope you found this seminar valuable. If you have any comments on how we can improve our web seminars, please pass those along as well. Oh, I see one more question came in. Let's just check it. Oh, it was a thank you. You're welcome, and I thank you. Thanks for your attendance, and goodbye.